In this lecture, we're going to talk about limit laws and how to utilize them to actually compute limits of complex functions. Before we do the general cases, let's consider two of the simplest possible functions, a constant function and a function y equals x. So let's take a look at the constant function and its graph. We already have a fairly good understanding of how to compute the limits from the graphs here. And the graph of this function, of course, is simply a horizontal line at the height of 7. So if I am going to compute different limits, I can simply look at the graph. I know that this function is a straight line. There's no hidden oscillations or holes anywhere here. So in terms of computing the limit of this function, as x approaches -2 is somewhere here, I will approach x from the left and the right of -2, and I'm going to go along the function to do so. So as I go along the function towards -2 from the left, I approach the height of 7, and as I go towards -2 from the right, I still approach the height of 7, because I, of course, approach just this spot on the function. So the answer here is going to be simply 7. What if x approaches 0? So I am approaching 0 from left and right. I'm going to move along the function. So I'm going to approach the height of, well, still 7. What about if x approaches 5? So this point right here. You notice that, of course, the justification is going to be the same, that the function limit simply approaches 7. In fact, it doesn't matter what value x approaches. The limit for all the possible values that x approaches of this constant function is going to be 7. So that's quite convenient. I know that if my function is simply a constant, the limit of it is always going to be the actual value of that constant, independent of the value of x that I plug in. For the next case, let's consider y equals x, so this diagonal function here. If I'm going to take a look at x approaching -2, so it approaches -2 right here from the left and from the right. This will mean that the function value approaches this point right here. But because my function is y equals x, if x is -2, then the corresponding value of y here is also going to be -2. So as x approaches -2, y also approaches -2. If x approaches 0, we can reason very similarly that y will also approach 0. If x approaches 5, then y would also approach the value of 5. In fact, it becomes fairly clear that if x approaches any value of a, then the y, simply by the virtue of being equal to x, will also approach this value of a. These two simple cases lie at the foundation of how we can start calculating limits algebraically using the actual formulas of the actual functions. Now, of course, these two are very simple functions, so we need to expand our computations of limits to more complex functions. And we're going to do so by introducing limit laws that will simply build on the compositions of the different functions. These apply to all limits of all the functions that actually have their limit existing at a particular point. I'm not going to prove them or justify them. Please take a look at the book to see a more careful treatment of why these actually work. But the limit laws essentially say that if I have two functions that are well behaved around point A, in the sense that their limits at point A exist, so again, remember that limits care about what happens near a point, not at the point. So near the point A, both functions are nicely behaved. Then you can do all kinds of things to the limits. So if you're computing the limit of a sum, f plus g, you can actually break them apart and compute the limit of the first function, limit of the second function separately, and then add the limits together. Okay? Same with the difference, same with the times. Again, instead of computing the product of the functions first, you can compute the limits separately and then take the product. Same with the quotient, except for, of course, in the quotient, the bottom cannot be 0. And then there's this very convenient, there are these two really convenient laws that can actually be derived from the above ones that say, look, if you have a function f of x multiplied by some constant, and this constant does not depend on x, limit is computed when x approaches something. So if inside you have a constant that doesn't depend on x, you can take this constant outside of the limit. Okay? And if you have a limit of a function to some power, then again, you can compute the limit separately and then raise the entire limit to the power, as opposed to just raising the function to the power first. Okay? And we'll see how these apply shortly. These are limit laws. Let's talk about how to actually compute limits from an algebraic expression. So the first rule of limits, I call it just plug it in. The book calls it direct substitution rule. So direct substitution rule says if the function is nice, then you just plug it in and the value you get is the value of the function. So what does it mean to be nice? It means not have any unexpected behaviors at the point. So remember from last video about when does limit not exist? It's things like holes, like jumps, like asymptotes, like oscillations. So if we're not talking about those cases, we will call the function nice. So nice means no holes, no jumps, let's say. No finite jumps, non-infinite jumps, so no asymptotes. So most of the functions that we will work with are generally nice except for at certain points. So for example, polynomials are always nice functions, right? They never have holes or asymptotes. Rational functions are mostly nice except for at the asymptote. So rational functions except for when the bottom, the denominator, is equal to 0. Things like trigonometric functions, so for example, sine and cosine are nice smooth curves. You can always calculate any limit along them, except for, of course, like tangent already starts to have asymptotes. Things like this, like exponential functions, they have mostly, they're mostly well-behaved logarithms and so on. So the more functions we see, the more functions we will analyze with respect to holes, jumps, and asymptotes. So if you can plug it in and there are no issues, then you're done. You got lucky. This is a nice function. This is just the value of the limit that it is. The second rule of limits is just plug it in anyway, because plugging it in will help you diagnose the problem. Helps diagnose the issue. And once you know what the issue or problem is, you can actually solve it, right? If you have no idea why this function is not nice, then there's no way to actually approach it. Once you plug it in and you see what is creating an issue, we can target that issue. Once you diagnose the problem, there are a couple of ways to actually target the issues. You can try to simplify an expression. So it's things like factor things out or multiply by a conjugate are the two most common techniques. Or we can try to justify or by conjugate, we can try to justify or reason out why a limit is a certain value. Okay, and we'll see examples of both shortly. So let's take a look at the first one, where we have a rational function and we're asked to compute the limit at 3. So again, first rule of limits, plug it in. Let me write this down. Plug it in. So we're going to take the value that we're given, x approaches 3. So I know that once again, when the limit is computed at x approaching 3, it's not actually at 3, it's just around 3. But let me plug in 3, and if there is no problem at 3, then the limit is as the function value. So if I plug in 3, x equals 3 into all of these x's here, so 3, 3, 3, what am I going to get? 3 squared is 9, 9 plus 3 is 12, minus 12 is 0, so the top is 0, and then the bottom is 3 minus 3, so also is 0. Well, that's an issue. Now, I'm going to put this in square brackets because this isn't really quite the number that I'm actually computing, right? I'm not really supposed to be plugging in 3. Limit is what happens around 3. So this isn't really 0, it's a number close to 0, and I have no idea how close it is. In particular, I have no idea how close it is with respect to this other 0. I don't know what the relationship of these two zeros is. Is the top number much bigger than the bottom number or the other way around? Okay, but this allows me to diagnose the problem here. This 0 on the bottom is really an issue. I cannot divide by 0. That's not allowed. So this x minus 3 on the bottom is creating the problem. So what can I do to get rid of it? Well, let's take a look at this limit to begin with. I can see that the top I can probably factor out. So let's try that. So we're going to try to factor. And what are we going to get? If the limit stays there, because we haven't computed yet, the top factoring out gives us x minus 3, x plus 4, and the bottom stays x minus 3. Well, this is fantastic news, because now I can cancel out the x minus 3's. And remember that it was exactly the x minus 3 that was creating the 0 on the bottom that did not allow me to compute the limit. Okay, so once that gets cancelled, I can rewrite this as limit of x plus 4. I've cancelled out my problem. Now I have myself a new limit, which means that I can try to plug it in again. My original problem should not exist anymore, so maybe I have no issues whatsoever. Okay, so we're going to plug it in again. And what do we get? Well, if I plug in x equals to 3 into this x here, I get 3 plus 4, which is 7. Okay, no issues. If you get a number, that's your answer. Okay, so it is important to note here that this function isn't actually the same as x plus 4, because this original function did not exist at 3. It has a hole at 3. Right? And so this function doesn't quite describe this function perfectly at 3, but it describes it well everywhere else. So I can compute the limit at 3, even though my original function does not exist at 3. Okay? Okay, let's take a look at the second one. And again, we have a limit. The very first thing you're going to do is plug it in just to see what happens. And here, what are we going to get? If we plug in 0, x goes to 0, so if I plug in 0 here and 0 here, root of 9 is 3, 3 minus 3 is 0, divided by 0. So once again, I get 0 over 0. Once again, I'm going to put it in square brackets, signifying that I'm not actually computing 0 divided by 0. I'm computing something close to 0 divided by something close to 0. But because I cannot compute that directly, now I have an issue. And again, it's actually the 0 on the bottom that's an issue. I can divide 0 by something, but I can never divide by 0. Okay, so this 0 on the bottom comes from this x being on the bottom. So I would like to somehow simplify or massage this expression, hopefully in order to get rid of the x factor on the bottom. Okay, so let me take a look at this guy here. What can I do? I cannot do any kind of factoring on the top. It's not a polynomial. I mean, here it was nice and quadratic. This one is not a polynomial function, so I can't really factor. It would be really nice to get rid of the square root though, wouldn't it? And this is where you're going to have to be extremely careful. I like to say that simplifying is like putting makeup on. It can change the way it looks, but it should not change its value. Okay, so you cannot just decide to plop a square on top of it, because now the expression is not the same as the old expression, and simplifying should not change the value. Not to mention that actually plopping square root on top will not get rid of the square root. So the one common technique to get rid of the square root is to multiply by conjugate. So to multiply by the exact same expression, but instead of the minus separating the two pieces, you're going to have a plus. Because we're going to multiply by the conjugate, in order to keep the value, we also have to divide by the conjugate, okay? So your next expression is actually going to be your original function written out fully. So minus 3 all over x multiplied and divided, again, so as to not change the actual expression, by the function's conjugate. So the exact same thing, but with the plus in the middle, okay? Now, please pause the video and actually try to factor things out on the top, okay? So on the top here, maybe I'll put in the brackets, I'm going to actually FOIL the whole thing out. So I have to multiply everything throughout, and I'm going to get one long expression, but things are going to really simplify quite well. So pause here and actually do the algebraic manipulations yourself. As I've mentioned before, math is not a spectator sport, so watching me do a bunch of algebraic manipulations is not actually going to make you any better at it. So please pause and try to open up the brackets, try to simplify. Okay, so now that I trust you've actually tried this for yourself, I'm going to write down the expression that you should have gotten. Once you do a bunch of these, you will notice a pattern, or maybe if you practice this quite a bit in grade 12, you already know that the difference of squares will give you the square of the first term minus the square of the second one. Here, though, foiling it out, I see that the first thing I get is root of x plus 9 times root of x plus 9, which is x plus 9. And then I'm going to get the root times 3 and the root times minus 3, so they will cancel each other out. And the last term is 3 times negative 3, which is minus 9. But my bottom is going to be this entire expression, okay? Maybe let me move it here. Nope, won't fit. Okay. All right, so what happens here now? These 9s can go away, plus 1 and 9 minus 9. And so what I have left is limit as x goes to 0, x over x, and my remaining conjugate on the bottom. And now this is also really great too, because now that I have x by itself as a factor on top, I can cancel it out with the x on the bottom. Okay? And remember, why this is really great news is because this 0 coming from this x on the bottom was exactly the reason that we couldn't just plug in and compute the limit in the first place. Now I've canceled this x out, so hopefully that issue went away and I can just plug it in and get a number. Okay? So what happens here? Well, x on top went away, and there's 1 that was remaining, so now I can plug it in. What am I going to get? Actually, let me just rewrite this. Limit as x goes to 0 of 1. Note that I've canceled out x. I didn't cancel out all of the top. There's still going to be 1 remaining, so x plus 9 plus 3. And if I plug it in now, all I'm going to get is 1 over root 9 plus 3, so 1 over 6. That's fantastic news. I just got a number, which means that there were no more issues. I've managed to simplify, massage this issue away. So now I can just compute limit as a number. Now let's take a look at some limits where we just have to plug things in and be able to justify it. So there's nothing really to simplify, and therefore we're going to have to apply some other kinds of justifications to them. Let's take a look at this first one. So as x goes to 0, I'm interested in the fraction 1 over x. What happens here if I plug it in? I'm going to get 1 over 0. And again, that's not something that I can compute, so I'm going to put it in square brackets. But what does that really mean? I'm dividing 1 by a really, really small number. Okay? So let's pretend you have yourself a pizza, and you're dividing it into tiny, tiny little pieces. How many pieces are you going to get? Lots. The smaller the pieces, the more of them you're going to get. Right? And because it's a limit as x goes to 0, you're actually looking at tiny, teeny, tiny pieces. So you're going to get a ton of them. The mathematical way to describe a ton of them will be to say infinity. And the symbol for that is sort of a sideways 8. Okay? On the flip side, what happens if you do the exact opposite? So what if x goes to infinity and you're wanting to compute 1 over x? So I have 1 over infinity essentially. And again, I'm going to put this into square brackets because infinity is not quite a number. It is a concept of a number that is larger than anything that you can think of. So what happens here is I'm dividing 1, so again, 1 pizza, let's say, into a ton of pieces. How big is each piece going to be? If I'm dividing into many, many, many pieces, the more pieces I divide into, the smaller each piece is going to be. So this is like the exact opposite of the question before, where now I'm going to get a 0. This is also helpful to consider in terms of a graph. So for example, for 1 over x, the graph of a function looks like this. Whoops. These guys are asymptotes, and they're symmetric. Let's pretend this is nice and pretty and smooth, right? And so as x approaches 0, from the left or from the right here, notice that I didn't actually specify, and so my infinity doesn't have a plus or minus sign. So if I'm approaching, let's say, from the right, as I go toward the graph, my graph, the closer I get to 0, the higher my graph climbs. So the closer I get to infinity on that side. On the other hand, if I approach infinity, so that means that I keep going further and further along the x-axis. So I keep going further and further along here. The closer and closer to the x-axis my number is going to become. If I divide by 1,000 and then 10,000, a million, 10 million, the smaller my outcome is going to be. Okay, let's take a look at these other two. So again, first rule of limits, plug it in. So what happens if I plug it in? I get 2 to the 0 over 7. What is 2 to the 0? Any number to power 0 is 1. So it's 1 over 7, and we're done. There's no issues here. There's no problem having 0 in the power. The last example here, again, first rule of limits, plug it in. So plug it in, I get 0 over 2 to the 7th. Dividing 0 by anything except for 0 will give you 0. If you have no pizza, doesn't matter how many friends you get, you're still not going to be able to eat it, right? So 0 divided by something is 0. You can divide 0, but you cannot divide by 0. So be careful about that. Let's take a look now at our very first application here, Lorentz formula. Hendrik Lorentz was a Dutch physicist he was actually a Nobel Prize laureate. He won a Nobel Prize in 1902. He's one of the most influential physicists of our time. He's the one that laid foundations for special theory of relativity, as well as some of the quantum theory that physicists are working on today. So this is the formula that is known as Lorentz formula, and it describes the length of an object at certain velocity. Okay, so the formula has a bunch of constants and no real numbers, so let's label all the known quantities, or all the quantities that are actually in the formula. So this v is the object's velocity or speed. This c is the speed of light, so everything is compared to the speed of light. This L0 is the object's initial length. So let's say I take an object, my car, and it starts traveling faster and faster. What the question is asking is, and what the formula is actually giving us, is the length of the car as perceived by an observer as it moves at a certain speed. Now, the question isn't actually asking to compute the length at a certain speed. It's asking to compute the limit of this length as the velocity approaches the speed of light. So let's first of all write out in words what is it that we're trying to compute. There's always two parts to a limit. There is what it is that you're trying to compute and where are you computing it at. So what is it we're trying to compute? We're trying to compute L, which is the length of an object. Okay, we're trying to compute it in the limit, which means that this is the length the object approaches, right? That's what we're trying to compute, the length that the object actually approaches as, and then where are we computing it at? We're computing it as velocity approaches the speed of light, and it's important to note here that it's approaching the speed of light from the left. So my object, my car, let's say, accelerates toward the speed of light, not decelerates towards it, okay? So length of an object, we're computing the length the object approaches as its speed approaches the speed of light. I don't know if you guys can hear, but the crows outside of my window are going crazy. So if you can hear that on the video, I'm sorry. There's nothing I can do about them. Okay, the first rule of limits, we're trying to plug it in. But now the first thing we're going to try to plug in is to actually replace this L with a formula for it that is given by the Lorentz formula. So limit as v goes c from the left of L, which is given by L0, 1 minus v squared over c squared. Excellent. Now, in plugging it in, here I'm going to have to be a little bit more careful for two reasons. First of all, I'm asked to plug in something that is c from the left. So not c, but a quantity that I know is really, really close to c, but smaller than c. So I can plug in c, but keep in mind that whatever it is that I'm plugging is just a little bit smaller. And the other problem is the square root. This is where normally some issues can arise. Either division by 0 or computing square roots of negative numbers. Those two operations are not allowed. So if all of a sudden I have a square root where whatever is underneath is negative, that's going to be a problem. So let me plug in c minus and keep that in mind as we're doing some of these computations. Plug it in. Okay, so what am I going to have? I'm going to have L0. I'm going to put it in square brackets if there is an issue. Otherwise, I'm just going to keep it as is. So I am plugging in v goes to c minus. So I'm plugging in c instead of v. C is an actual number. Speed of light is a known constant, right? So I'm plugging that in instead of the velocity. Whoops. So I'm going to have 1 minus c squared over c squared. Okay, pause here and make sure you actually understand that I just replaced this v with the c. Now, the one small nuance here is, again, I'm actually replacing, maybe I should put it in a slightly different color, the c guy here. This is the one that I replaced, right? This c, I know, is a value that's just a little bit smaller than c. So when we're analyzing, we're going to have to take that logic through with us, okay? So let's see. Here I have c squared over c squared. A number divided by itself is always 1, but here I know that the number on the top is just a little bit smaller than c, right? So this quantity actually approaches, this guy approaches 1, but from the left. It's just a little bit smaller than 1, which is in fact very good news, because now I'm doing 1 minus something slightly smaller than 1, like 0.99999 or whatever, right? Which means that the outcome of this operation is positive, which means that I will be able to actually take a square root of it. I'm not taking a square root of a negative number here, so we're all good. Okay, now with that in mind, I can actually compute what happens next, right? So I'm going to have L naught square root of 1 minus 1, because that's what my quantity approaches. 1 minus 1 is 0, a positive 0 here, right, on the positive side. So it's going to be L naught times 0, which is 0. Okay, so my ultimate answer here is that as an object approaches the speed of light, its length approaches 0. That makes sense. Try to justify that to yourself. Getting better at doing limits means doing more limits. Now, oftentimes, or really almost always, we're not actually told what to do, whether to simplify or justify. So in this case, we are going to have to figure out what the approach should actually be. Now, let's start off with this one. So we have limit as x approaches 3 of the big rational function. Again, remember, by the first rule of limits, the first thing we're going to do is plug it in. And what are we going to see here? If we plug this in carefully, we will see that on top we get a 0, and on the bottom we also get a 0. So once again, we can record it, but inside the square brackets to indicate that we know we don't actually mean 0, we mean something very, very close to 0. However, this can result in a variety of different answers, so now we have to decide what it is that we're going to do. Note that we've plugged 3 into the two polynomials, one on top and one on the bottom. And we produce 0 both times, which means that 3 is actually a root of both the top and the bottom. Now on the bottom, it's very clear that it's a root because it's a linear polynomial, but on top, that means that 3, when you plug in, is a root, which also means, if you, again, dig into your pre-calculus background, that x minus 3 is a factor of the polynomial on the top. So what we're going to have to do here is factor it out. Now, in this particular case, there is a number of ways you can do it. First, you can actually notice that x is present in all 3 different terms. And so first thing you can do is pull 1x out and end up with x squared minus 6x plus 9. If you have Wolfram alpha on hand, you can also just ask it to factor the original polynomial, or you can proceed by hand here for extra practice. And then we have to factor in the second polynomial. You can think of 2 numbers that have to multiply to be 9 and add to be negative 6. And what you're going to get is x minus 3, and x minus 3 again. So on top, we actually have x minus 3 squared. And at the bottom, we still have our x minus 3. Now notice that now that we have factors, we can cancel them as factors of the top and the bottom, and now I can rewrite my limit. Also, be very careful about the fact that while you still have x's here, you will also have the limit trailing all the way through. So don't accidentally drop it, because this expression in the limit is not equal to this expression without the limit. Okay, so what do I have left? I have x times x minus 3. Now, it seems that I've arrived at a natural stop point in the simplifications, which means that the thing to do now is, again, to plug it in and then see if the situation has actually improved. So plug it in, and if it hasn't, then we will have to simplify more. Now, if I plug 3 in now, I get 3 times 3 minus 3, or 0, which of course overall gives me 0. So here the answer is 0. This limit of this function is equal to 0. Okay, let's take a look at the next example. I strongly encourage you for all of these examples to pause the video first and try them out. You've already seen all of the techniques that I'm going to employ in the next few examples, so this is really just for extra practice, and it would once again be extremely beneficial if you practice it for yourself at first. So, first rule of limits, plug it in. What do we get in this case? Unsurprisingly, in this case, if we plug x equals to 27 on both top and the bottom, we're going to get 0 over 0. Now, how are we going to now simplify this expression? As opposed to the one on top, these were polynomials, so we could think about factoring. These, the top is a polynomial, but the bottom has a square root, so it's not a polynomial function. So really, we would like to somehow get rid of the square root, and the only way we can do that is to multiply by a conjugate. So this is going to be my technique here, multiply by a conjugate, and of course, I need to multiply by the conjugate that contains the square root. So my top will keep x minus 27 for now. My bottom will keep x plus 9 minus 6. And then I'm going to multiply this entire thing by the conjugate of the denominator. So x plus 9 under the square root. And the conjugate means that the sign between the two terms is changed, so plus 6. But of course, I would like to keep writing equals all over the place. So if I multiply by something on the bottom, I need to multiply by that same thing on the top. So essentially, I'm actually just multiplying by 1. Now, this will allow me to expand the brackets on top and on the bottom. And the reason that this works is because what I end up with on the bottom is the difference of squares formula. So I'm going to skip a step here in the simplifications because once again, I both encourage you to actually do them yourself by hand, and this is a very specific pre-calculus skill. So if you are unsure of how to do it, look it up in the pre-calculus refresher. But essentially, if you have two different terms, this is kind of like a and minus b, and this is a plus b, the multiplication will result in a squared minus b squared, the difference of squares. So the first term squared, square root of x plus 9 squared, will simply result in x plus 9, minus the second term squared, 6. 6 squared is 36. Okay, I can of course do the addition here, plus 9 minus 36. I'm going to skip a step in rewriting this. Minus 9 plus 36 will result in minus 27. And now this is really quite excellent news because notice now I have the factor of x minus 27 on top and I have a factor of x minus 27 on the bottom. So I can cancel them each out and my new expression will now become limit as x goes to 27. Again, notice how I'm still rewriting this limit because I still have not plugged in the value in the limit for x successfully. And the only thing I have left is square root of x plus 9 plus 6. Now remember that I had 0 over 0, and now I've successfully gotten rid of the entire denominator. So I can't possibly have 0 on the bottom, much like actually in the case above, in the example above. So that means that I have to once again try to plug it in and then see if my situation has in fact improved, which I believe it has because of the absence of the denominator. If I plug it in, what do I get? 27 goes in for x, so I'm going to get square root of 27 plus 9 plus 6. Be careful about these simplifications as well, because this square root doesn't mean square root of 27 plus square root of 9. So I have to add these two terms together first and then take a square root. 27 plus 9 is 36. Square root of 36 is 6. And then I have this is 6 here plus this 6 over here is going to be overall the value of 12. So that means that my limit that I was calculating from the beginning is actually valued at 12. Let's take a look at a few more. Once again, pause the video and try them for yourself. Just watching me do one after another doesn't mean that you will learn how to do them. Until you do 10 or 20 or 30 of these, you're not going to really be able to reproduce the results that I have without your own practice. Okay, so here's my first limit. This one has two separate portions, right? It's something minus something else. It's not one big fraction like the limits that we've seen on the previous slide. However, the first rule of limits does not change. The first thing we're going to do is plug it in. What happens when we plug it in here? So my x goes to 0. So I end up with 1 over 0 minus 1. X is 0. 0 squared plus 0 is still 0. So still 1 over 0. So my issue here, of course, is there is only 0 in the denominator. So as we've discussed previously in this lecture, if I have just 1 over 0, it means that I'm dividing 1, a constant, by something very, very small. So altogether, this will generally tend toward infinity. But now the problem here, of course, is I have two of these things. So I don't know which one of these infinities is bigger, the first one or the second one. Am I subtracting something small from something big, or am I subtracting something big from something small, right? I'm not going to be able to actually figure it out unless I form one big fraction out of the two of these pieces. So the thing that we're going to do here is, first of all, do the common denominators. I would like to be able to analyze this in one big fraction form. Now, once again, if this is a step that you were missing in your own simplifications, feel free to pause the video at this point and try this for yourself now again. Now, common denominators, once again, a very standard pre-calculus technique. So what are our common denominators here? Well, I could just multiply each part by each part, but I could notice something a little bit more efficient. So the first thing I can notice is if I simplify or factor this second denominator, it's actually x times x plus 1. So that means that my smallest common denominator is x times x plus 1, not x times x squared plus x, right? So that means that in order for me to have common denominators between these two fractions, I only need to multiply the first fraction by x plus 1. So that is what I'm going to do. As x goes to 0, so I have x plus 1 over x times x plus 1. Remember, when we're multiplying a fraction, we once again have to multiply the top and the bottom so that my expression overall does not change. 1 over x times x plus 1. Now that I have common denominators, I can bring the two fractions together. So I'm going to have limit as x goes to 0. On the bottom, I have x times x plus 1. And what do I have on the top? I will have x plus 1 minus 1. So I'll notice that 1's actually cancel each other out. So on top, overall, I will simply have x. And now I also notice that I can cancel the x on top with the x on the bottom. So now my expression becomes limit as x goes to 0. Once again, I haven't plugged in the value for x yet, so I still carry on my limit. I haven't evaluated the limit yet. And on the top, I seemingly have nothing, but that's because I've canceled out a factor. Remember that 1 is always a factor of anything. So I have 1 over x plus 1. Well, this fraction, this function, is essentially as simple as it can get involving x. So there are no obvious simplifications at this point. So the next thing to try is to, once again, plug it in. So see if at this point I've managed to get rid of the problem that caused me not to be able to simply evaluate the limit in the first place. And what do we have here? I plug in 0 in for x. I'm going to get 1 over 1, which overall is 1. Okay, so the value of this limit is equal to 1, which really means that this infinity was just 1 bigger than this infinity for x approaching 0. All right, next up, what do we have here? We have x to the 4th minus 81 divided by x plus 3. Again, first rule of limits, we're going to plug it in. Let's take a look at what that gives us. If I plug in minus 3 in top and the bottom, I'm going to get 0 over 0. So I know that x equals negative 3 is a factor of the bottom, which again is pretty obvious, but it's also the factor on the top. So I should be able to divide it out from there. You can, once again, utilize a computer system such as Wolfram Alpha or your calculator maybe to factor out the top expression. I'm going to do it in an old-fashioned way by hand. And what I'm going to employ here is going to be the difference of squares formula. It's always good to go back to basics and actually be able to perform some of these algebraic techniques sort of from scratch. So the difference of squares formula says if I have two squares, which I do here, this is x squared, and 81 is 9 squared, then I can actually break them up into the two conjugates. So in this case, on top, I'm going to have x squared minus 9 and x squared plus 9, all divided by x plus 3. Now I know that this hasn't really resolved my issue yet for sure because I still haven't canceled anything out. So my zeros will most certainly remain in this expression if I plug minus 3 in there now. So what else can I do? Well, this factor, there's nothing I can do about it. This has no solutions. If you set x squared plus 9 to be equal to 0, you can expand it out. You will notice that this results in x squared being equal to minus 9, which of course has no solutions. So I can focus my attention on this first factor, and I notice that once again, I can actually apply the difference of squares formula. So what I'm actually doing here is applying the difference of squares twice. So in this case, what I'm going to get is I'm going to break up the x squared minus 9 into x plus 3 and x minus 3. Okay, so this is just for this expression right here. And then I still have my x squared plus 9 remaining as a factor, and my denominator has not changed from x plus 3. But now I can of course see that I have x plus 3 on top and on the bottom as factors, so I can cancel them. They can cancel each other out. So overall, what I'm going to have left is limit as x approaches negative 3 of x minus 3 and x squared plus 9. Now, I know that I'm almost certainly at this point in time successful in simplifying the original issue away because I no longer have a denominator here. So I can plug the value for the x in, and again, I am fairly certain that this will result in the answer immediately. So if I plug this in, I'm going to get that this is negative 6. This is equal to 18. So altogether, I have minus 108. Okay, so the value of the limit for this function is minus 108. For every different type of algebraic limit, you might have to apply a different technique. So make sure that your algebraic toolbox is varied in the types of algebraic manipulations that you can perform. Now, as the last example in this class, let's take a look at one more application. Going back to Michaelis-Menten kinetics and their formula for the chemical reaction of the substrate and the enzyme. So recall that the speed of the reaction, which is denoted by S here, so let's record that, depends on the concentration of the substrate. So in this case, X is the concentration of the substrate. Okay, and we know that this is a Michaelis-Menten kinetics, which is also a linear Hill function, where A and B are simply constants. And what we're asked here is to find and interpret the limit as x goes to infinity of S of x. So let's first of all interpret what we are going to calculate. Doing the calculations first and then interpreting is another way to go, but I like to think of the meaning behind my calculations before I actually do the work. So what we have here is x approaches infinity. So the x that corresponds to the concentration approaches infinity. So the concentration is very, very large. And I am taking the limit of S of x, which corresponds to speed. So altogether, this means that I'm looking for the speed of the reaction as the concentration grows very, very large. as concentration of substrate in particular. So let's be precise. Substrate grows very large. Now I know that in reality, the concentration of the substrate cannot, of course, be equal to infinity, but this is my sort of idealized case. This is my long-term behavior. What happens if it does grow very large, but not specifiedly very large? We will employ similar techniques for thinking about long-term behavior in terms of time as well, when we let time go to infinity. Again, in reality, that's not something that we witness, but we would like to know what happens if we do let a process follow its natural flow as we model it. Okay, so let's replace s of x with the actual formula in the limit. So we have a particular function that we're looking at. So here I have ax over b plus x. So as the first rule of limits, we're going to try to plug it in, right? So the first rule of limits, being the first rule of limits, never changes. So if we plug it in, what are we going to get? On top, I have some constant times infinity. Well, that's going to produce infinity. And what do I have on the bottom? I have some constant plus infinity. That is also going to produce infinity. This is still not something that I can actually resolve immediately because I have no idea which infinity here is bigger. If the top is bigger than the bottom, then I'm going to have either infinity or some kind of number. If the bottom is bigger than the top, then I'm going to have either 0 or some kind of small number. Right? So this is one of the other, what are called indeterminate forms, and I cannot simply justify my way out of this. I have to somehow simplify the existing inside of the limit. There are a few different ways to go about these types of limits, and we will talk about limits at infinity more in the next class. But the, let's say, preferred, in some ways, by at least me in this course, way is to actually apply the power analysis. Not only because it is cleaner than other techniques in this particular case, but also because we've already practiced it so much. So I'm going to write here that we're going to work with power analysis. And remember what power analysis did is, in fact, we were doing exactly this, but in a less rigorous way. Now we can actually write in the limit the exact equal expression as opposed to saying what the function approaches in a very hand-wavy way for large values of x. As x goes to infinity, we're looking at the large values of x case. On top, remember, with Hill functions, we don't have a choice. Ax is the only term, so for large values of x, ax approaches ax. But on the bottom, we have two different terms. For large values of x, large powers of x will dominate, and this b being a constant corresponds to the power of x being 0, whereas this x being x corresponds to power of x being 1. The larger power of x is represented by x. And so by the power analysis, that's the term that we're going to keep. So once again, this is actually a more rigorous way of writing down the power analysis using the limit notation. And then our justification is now the familiar, well, x's will cancel. And so what I'm going to have is limit as x goes to infinity of some constant a. And remember, as per the very first slide in this lecture, a limit of a constant for any value of x is always going to be that constant. So overall, what that means is that the speed of the reaction as concentration of substrate grows very large approaches some constant a, which again, if you recall the graph of the linear Hill function, you will remember that the horizontal asymptote corresponded to the end behavior and a here, and of course signify that the speed of the reaction as the concentration grows infinitely large approaches that particular constant. Okay? It all comes around back full circle.